The year is 2025. A headline explodes across the world. A headline so profound, so utterly world-changing, that it instantly redefines the human story. It doesn't speak of war or politics or a new technological marvel. It speaks of a scent, a chemical whisper carried across 120 light-years of interstellar void, detected by the most powerful instrument ever built by humanity, the James Webb Space Telescope. The whisper is a molecule called Dimethyl Sulfide, or DMS. On Earth, DMS is a gas produced almost exclusively by life, by phytoplankton blooming in the oceans, by microbes in the soil. It is the chemical scent of a living world, and Webb found it, or at least a tantalizing hint of it, in the atmosphere of a distant water-rich exoplanet named K2-18b. This is not a drill. This is not speculation. This is the moment we have waited for since we first looked up at the stars. The first, tentative yet electrifying evidence that we are not alone. It is the moment the question of alien life moved from the realm of science fiction to the cold, hard data of astrophysics. But the story of K2-18b is not a simple confirmation. It is a labyrinth of scientific caution, instrumental noise, and a profound philosophical debate about what truly constitutes proof. It is a story that forces us to confront the highest bar in all of science, the standard of evidence for life beyond Earth. If the thought of an alien ocean teeming with life 120 light-years away has already sent a shiver down your spine, if you are ready to embark on the most important journey of discovery in human history, then you are in the right place. This is Cosmo Depth, and we are about to dive into the atmosphere of K2-18b, explore the strange new category of worlds it represents, and confront the staggering implications of the chemical scent of life. If you want to join us on this journey, if you want to explore the deepest, most mind-bending secrets of the universe, then take a moment, hit that like button, and subscribe to the channel. It's the easiest way to ensure you don't miss the next time we peel back the curtain on reality. Prepare yourselves, we begin. To understand the magnitude of the DMS dimethyl sulfide detection, we must first understand the world that hosts it. K2-18b is an exoplanet orbiting a red dwarf star named K2-18, located in the constellation Leo. Its discovery in 2015 by the Kepler Space Telescope was significant, but not immediately revolutionary. It was categorized as a sub-Neptune, a class of planet larger than Earth, but smaller than Neptune, a type that is common in the galaxy, but has no equivalent in our own solar system. Its size is about 2.6 times the radius of Earth, and its mass is approximately 8.6 times that of our planet. This places it squarely in a planetary-sized gap where the line between a rocky super-Earth and a gaseous mini-Neptune is blurred. But what truly set K2-18b apart was its orbit. It circles its star within the habitable zone, the region where temperatures are just right for liquid water to exist on a planet's surface. Its star, K2-18, is a cool, dim red dwarf, meaning K2-18b has to orbit much closer to receive enough warmth. It completes a full orbit in just 33 days. This proximity to a red dwarf, however, introduces the first layer of complexity to its habitability, a challenge we will return to later. The first hint of K2-18b's true nature came in 2019 when the Hubble Space Telescope detected water vapor in its atmosphere. This was a monumental finding, suggesting that the planet could indeed host vast quantities of water. But the question remained, where was the water? Was it a thin layer of liquid water on a rocky surface, making it a true super-Earth? Or was it a thick, high-pressure atmosphere of hydrogen and helium, with a deep, crushing ocean beneath, making it something entirely new? This is where the concept of the Hycean world enters the narrative. Hycean, a portmanteau of hydrogen and ocean, was a theoretical category of planet proposed by a team of researchers led by Dr. Niku Madhusudan at the University of Cambridge. They argued that sub-Neptunes, despite their size, could still be habitable if they possessed a massive, hydrogen-rich atmosphere overlying a global, liquid water ocean. The Hycean hypothesis was a radical departure from the traditional search for Earth 2.0. It suggested that life could thrive in environments far more extreme than our own, under crushing atmospheric pressure and in oceans heated by the greenhouse effect of a dense hydrogen atmosphere. K2-18b, with its size, its habitable zone orbit, and its detected water vapor, became the poster child for this new, exciting class of potentially life-bearing worlds. But the Hycean model was just a theory, a compelling possibility that needed confirmation. Enter the James Webb Space Telescope. JWST is not just a bigger telescope, it is a revolution in infrared astronomy. Its primary method for analyzing exoplanet atmospheres is called transmission spectroscopy. Imagine K2-18b passing directly in front of its star. As the starlight streams toward us, a tiny fraction of it passes through the planet's atmosphere. The gases in that atmosphere, methane, carbon dioxide, water vapor, each absorb specific wavelengths of light, leaving a unique chemical fingerprint in the starlight that reaches Webb's mirrors. By analyzing this faint filtered light, Webb can essentially taste the air of a world 120 light-years away. In 2023, the first JWST observations of K2-18b were released. They confirmed the presence of methane, CH4, and carbon dioxide, CO2. This was a crucial finding. The presence of both molecules, especially in a hydrogen-rich atmosphere, strongly supported the Hycean model. It suggested a world with an active, complex atmospheric chemistry, a world that could indeed harbor a deep, global ocean. The stage was set. K2-18b was almost certainly a Hycean world, but the 2023 data contained a subtle, almost overlooked hint. A weak 2 sigma statistical signal that might have been dimethyl sulfide. The signal was too weak to be claimed as a discovery, but it was enough to justify a follow-up. The scientific community held its breath. Then came the bombshell in 2025. New data, taken with a different JWST instrument, the Mid-Infrared Instrument, MIRI, provided a stronger 3 sigma statistical signal for the presence of dimethyl sulfide, DMS, and possibly its cousin, dimethyl disulfide, DMDS. The signal was still tentative, still short of the 5 sigma gold standard required for a definitive discovery, but it was enough to ignite the world. Why is DMS so important? Why did this single molecule send shockwaves through the scientific community? Because on Earth, DMS is the quintessential biosignature. It is the chemical that links the ocean to the atmosphere. It is produced by marine phytoplankton, which create a precursor molecule called DMSP. when the phytoplankton die or are grazed upon, DMSP breaks down into DMS, which then bubbles up into the atmosphere. It is the smell of the sea, the chemical breath of life. Crucially, on Earth, there is no known geological or non-biological process that produces DMS in the quantities detected on K2-18b. If you find DMS in an atmosphere, you have found life. The discovery was framed as a revolutionary moment. Dr. Madhusudan, the lead researcher, was careful to state that they were not claiming to have discovered life, but they were not shying away from the gravity of the moment. The best explanation for the data, they argued, was that K2-18b hosts life. The implication was clear. 120 light-years away, there was an alien ocean, and it was teeming with life. But the story of K2-18b is a cautionary tale, a reminder that the search for alien life is a marathon of meticulous scrutiny, not a sprint of sensational headlines. The initial excitement was quickly met by a wave of scientific skepticism, a necessary and vital process that separates a tantalizing hint from a confirmed discovery. The first challenge to the DMS dimethyl sulfide detection came from within the scientific community itself, focusing on the statistical confidence and the instrumental noise. The initial detection was at a 3 sigma level, meaning there was a 0.3% chance that the signal was a random fluctuation, a false positive. While this is a strong hint, it is not the 5 sigma certainty, a 0.00006% chance of error. That is the gold standard for a discovery of this magnitude. More concerning were the independent reanalyses of the JWST data. Several research groups, using their own data reduction and atmospheric modeling techniques, failed to reproduce the DMS signal. One prominent study found that the MIRI data, the very data that yielded the DMS signal, was highly susceptible to instrumental systematics, essentially noise and artifacts from the telescope itself. They found that depending on how the data was processed, the dimethyl sulfide DMS signal could appear or vanish. In their own preferred analysis, they found that 87.5% of their models did not favor the presence of DMS dimethyl sulfide. This is the hidden drama of modern astrophysics. The battle is not between telescopes, but between computer algorithms. The raw data from JWST is a complex noisy signal, and the final atmospheric composition is a result of sophisticated mathematical modeling. The controversy on K2-18b is a controversy over how to best clean the telescope's mirror, so to speak. A debate over which statistical model is the most honest representation of the truth. The second, and perhaps more profound, challenge is the non-biological production of DMS. The claim that DMS is a biosignature rests on the fact that on Earth, life is the only known source in the quantities observed. But K2-18b is not Earth. It is a Hycean world, a high-pressure, hydrogen-rich environment orbiting a red dwarf star. Scientists quickly pointed out that DMS has been detected in comets and in the cold, dark gas clouds between stars. While these sources produce DMS in tiny trace amounts, they prove that nature can create the molecule without life. Furthermore, laboratory experiments have shown that UV light shining on a simulated exoplanet atmosphere can produce DMS through photochemical reactions. The question then becomes, can the extreme environment of a Hycean world, with its dense hydrogen atmosphere and intense radiation from a red dwarf star, produce DMS in the massive quantities detected on K2-18b. The original research team argued that the non-biological processes they modelled could not account for the high concentration, but the burden of proof is immense. To claim life, scientists must not only prove the signal is real, but they must also exhaustively rule out every single non-biological explanation, no matter how exotic. This brings us to the standards of evidence for life beyond Earth. The scientific community has established a rigorous, multi-step framework for making such a claim, and K2-18b is currently stuck at the very first step. Have we detected an authentic signal? The answer, for now, is a resounding maybe. The story of K2-18b is a mirror reflecting the entire history of the search for extraterrestrial life. It is a history littered with tantalizing hints that ultimately faded under scrutiny. The Martian canals seen by Percival Lowell, the WOW signal from the Big Ear radio telescope, and the controversial detection of phosphine on Venus in 2020. Each one was a moment of breathless excitement, followed by the slow, grinding work of verification and debunking. The phosphine on Venus, for example, was initially claimed as a biosignature, only to be later attributed to instrumental error and misinterpretation. K2-18b is the latest and most compelling chapter in this history. It is a test case for the entire field of astrobiology, a moment that will define the next decade of exoplanet research. The controversy surrounding DMS is not a sign of failure, but a sign of the scientific process working exactly as it should, with a healthy dose of skepticism guarding the gates of the most profound discovery imaginable. But the story of K2-18b is far from over. The planet itself is a fascinating world, regardless of the life debate. It is the prototype for the Hycean world, a concept that has fundamentally expanded our view of where life can exist. The Hycean model suggests that life might not need a rocky surface like Earth. It could thrive in the deep global oceans of these sub-Neptunes, protected from the harsh radiation of their host stars by a thick, hydrogen-rich atmosphere. The ocean on K2-18b is theorized to be a high-pressure, high-temperature environment. A world where the water is not just liquid, but possibly supercritical. A state where it behaves like both a liquid and a gas. The pressure at the bottom of this ocean could be immense, and the temperature could be high. But life on Earth has shown an astonishing ability to adapt to extremes. Extremophils thrive in the crushing darkness of our own deep-sea hydrothermal vents, in boiling hot springs, and in the frozen deserts of Antarctica. The life on K2-18b, if it exists, would be an exo-extremophil, a form of life that has evolved to exploit the unique chemistry of a hydrogen-rich, high-pressure ocean. The hydrogen atmosphere itself is a key to the Hycean world's habitability. While a red dwarf star is cooler than our Sun, it is also prone to violent flares and emits intense ultraviolet radiation. A thin, Earth-like atmosphere would be stripped away by this stellar fury. But the massive, hydrogen-rich atmosphere of K2-18b acts as a colossal shield, protecting the ocean beneath and maintaining the temperature stability required for liquid water. However, the red dwarf star also presents a major challenge: tidal locking. K2-18e orbits so close to its star that it is likely tidally locked, meaning one side of the planet faces the star in perpetual day, while the other side is locked in eternal night. This would create extreme temperature differences. with the day side potentially boiling the ocean and the night side freezing it solid. Let's delve deeper into the intricate dance of a tidally locked Haitian world. The day side, perpetually bathed in the light of its red dwarf star, would experience a constant influx of energy. This energy would heat the upper layers of the ocean, potentially creating a runaway greenhouse effect. The water would evaporate, rise into the atmosphere, and then be transported to the night side. On the night side, in the eternal darkness, the water vapor would cool, condense, and fall back into the ocean as rain or snow. This global weather pattern, a colossal, planet-spanning convection cycle, would be the lifeblood of K2-18b, preventing the night side from freezing solid and the day side from boiling away. The Haitian model counters this by suggesting that the massive atmosphere and the deep ocean would act as a colossal heat distribution system, circulating heat from the day side to the night side, moderating the temperature and maintaining a global liquid ocean. The Haitian world, therefore, is a delicate balance of extremes, a testament to the diverse ways a planet can achieve habitability. The search for life on K2-18b is not just a search for a molecule, it is a search for a new paradigm of life. It is a search for the universal laws of biology, the rules that govern how life arises and evolves, regardless of the planet it calls home. The DM's controversy is forcing astrobiologists to rethink the entire concept of a biosignature. A biosignature is a substance or a phenomenon that provides scientific evidence of past or present life. The ideal biosignature should be a smoking gun, a molecule that is so complex or so abundant that it is virtually impossible to produce without a biological process. DMS was thought to be a strong candidate, but the non-biological discoveries have weakened its case. This has led to a renewed focus on atmospheric disequilibrium. The most robust biosignature might not be a single molecule, but a strange, unstable mix of gases that could only be maintained by a living system constantly pumping out waste products. For example, on Earth, we have a massive amount of oxygen and methane coexisting in our atmosphere. These two gases are highly reactive and should quickly destroy each other. The only reason they persist is that life, plants, and microbes is constantly replenishing them. Finding a similar, highly unstable mix of gases on an exoplanet, even if the individual gases are not DMS, would be a much stronger indicator of life. The future of the K2-18b investigation will focus on this disequilibrium. Future JWST observations will not just look for DMS, but for a whole suite of molecules, including ammonia, phosphine, and sulfur dioxide. The goal is to build a complete chemical profile of the atmosphere, a complex puzzle that only a living system could solve. The story of K2-18b is a profound reminder that the search for alien life is a conversation between Earth and the cosmos. We are using the only example of life we know, our own, to search for life we have never seen. This is the carbon chauvinism problem. We assume that alien life will be carbon-based, water-dependent, and produce familiar biosignatures. But what if life on a Haitian world is based on a different chemistry? What if it uses a different solvent than water, or a different backbone than carbon? The sheer size and pressure of K2-18b's ocean could lead to forms of life that are utterly alien, forms that we might not even recognize as life. The Haitian world is a challenge to our imagination. It forces us to move beyond the search for Earth 2.0 and embrace the possibility of Life 2.0, a new, more robust, and more diverse form of biology that thrives in environments we once considered uninhabitable. The controversy surrounding K2-18b is a necessary step in this evolution. It is the moment we realize that the bar for proof of alien life must be higher than any other scientific claim. It must be a claim that can withstand the most rigorous scrutiny, a claim that can survive the inevitable reanalysis and debunking attempts. The story of K2-18b is a story of hope, caution, and the relentless pursuit of truth. It is a story that will continue to unfold over the next decade as JWST continues to stare into the atmosphere of this strange, water-rich world. The next phase of the K2-18b story involves the confirmation and characterization of the planet's atmosphere. The scientific community is demanding more data, specifically more observation time, with JWST's MIRI instrument to push the DMS signal past the 5 sigma threshold. But the hunt does not rise or fall on dimethyl sulfide alone. Methane and carbon dioxide are already nailed down with high confidence, and the exact ratio between them is a whisper that could reveal everything. In a hydrogen-rich sky, those two gases behave like a planetary thermometer and pressure gauge, hinting at the hidden ocean's depth, temperature, and whether chemistry down there is quiet or alive and restless. At the same time, astronomers are chasing ghosts in the data, clouds and hazes. A single thick deck of aerosols can blur or completely erase the spectral fingerprints we're trying to read. Early JWST observations suggest K2-18b's atmosphere is surprisingly clear, almost too clear for a water world, but the jury is still out. Upcoming observations will map the vertical structure of its air column layer by layer, hunting for reflective cloud tops or high-altitude photochemical smog that could be masquerading as DEMS. Until those layers are accounted for, every claimed molecule remains probationary. The real endgame is not one miraculous molecule. It is an entire atmospheric portrait so bizarre, so stubbornly out of chemical equilibrium, that the only reasonable explanation left standing is life. This is what researchers now call a Tier 3 biosignature, a self-consistent model where dozens of gases, their abundances, their vertical distribution, and their photochemical interactions all point to a single conclusion, and geology alone cannot get you there. That is the summit K2-18b must still climb, and looming behind the planet itself is its star, a dim, crimson red dwarf, the most common type of sun in the Milky Way. 3 out of every 4 stars we can see are just like K2-18, cool, long-lived, and absolutely everywhere. If even a modest fraction of their sub-Neptunes turn out to be Hyson worlds with stable, life-friendly oceans, then the galaxy is not merely sprinkled with habitable real estate, it is drowning in it. Yet red dwarfs are moody landlords. They spend their youth throwing tantrums, violent flares, and coronal mass ejections that can double the star's brightness in minutes and flood nearby planets with X-rays and ultraviolet fire. A naked rocky world would be sterilized in a geological heartbeat. The Hycean shield, hundreds of kilometers of dense hydrogen and a global ocean, might just be thick enough to absorb the punishment and keep the water liquid and the chemistry cooking. Any life that arose there would have to be forged in a harsher crucible than Earth life ever faced. Radiation hardened, flare adapted, perhaps even using those deadly stellar outbursts as an energy source, the way our own phytoplankton harvests sunlight. In other words, if K2-18b truly is alive, it is not hosting gentle Earth-like plankton drifting in tranquil seas. It is hosting survivors, organisms tough enough to laugh at the fury of a red dwarf sun and still fill an entire ocean world with their chemical breath. And if that ocean is indeed breathing dimethyl sulfide across 120 light-years of interstellar night, then the galaxy's most common planets may also be its most alive. The data keep coming. The debate rages on. But one thing is already certain. K2-18b has forever changed the question we ask when we look at the sea of red stars filling the night sky. It is no longer, could something live there? It is, how much life is already out there, and how different is it from everything we thought we knew? This realization has ignited an entirely new frontier in astrobiology, the study of stellar flare resilience. Researchers are now modeling, in exquisite detail, how the violent outbursts from K2-18's red dwarf sun slam into that thick hydrogen envelope, how much deadly radiation actually reaches the hidden ocean below, and what kind of biology could not just survive but perhaps even thrive in such a hostile light show. Some speculate that any life down there might be radiotrophic, literally feeding on the high-energy particles the way plants feed on sunlight, or that it has evolved superpowered pigments, deep crimson or black, capable of turning lethal, UV and X-ray blasts into harmless heat. Imagine vast alien plankton blooms that pulse brighter every time their star throws a tantrum, turning apocalyptic flares into a global feast of energy. K2-18. B stands as a humbling testament to the universe's boundless imagination. It mocks our tidy definitions of habitable zone, laughs at our obsession with rocky, Earth-sized worlds bathed in gentle yellow sunlight, and forces us to confront the likelihood that the most common homes for life in the galaxy are nothing like home at all. It has shattered the old blueprint and handed us a far wilder one. Oceans that might never see a single star directly. Chemistry playing out under thousands of kilometers of crushing hydrogen. Biology forged in pressure and darkness and periodic firestorms from above. The long road to confirming or refuting the DM's whisper has already transformed the field. It has drilled into every researcher the brutal necessity of caution, the absolute requirement that the greatest claim in science must survive the fiercest skepticism. Every line of data will be reanalyzed, every model stress-tested, every alternative explanation chased to exhaustion. That grinding rigor is not a flaw. It is the only armor we have against self-deception when the stakes are nothing less than rewriting humanity's place in the cosmos. Yet beyond the labs and the telescopes, something deeper is stirring. A 3 Sigma hint from a world 120 light-years away is still just a ghost of a possibility. But it is the clearest ghost we have ever seen. For the first time in history, the ancient question scratched into cave walls and cathedral domes, "Are we alone?" has received something that feels, however faintly, like an answer. A whisper across the void that says, "Maybe not." That whisper carries weight no headline can measure. It is the kind that quiets wars in the mind, that makes borders on maps feel suddenly childish, that reminds 8 billion people sharing one fragile planet that we might, after all, have neighbors. The search for life on K2-18b is more than spectra and statistics. It is the slow, careful opening of a door we have been rattling for millennia. Behind it could be an ocean full of strangers, or simply more questions. Either way, we are no longer shouting into silence. We are listening, and for the first time, the universe just might be listening back. The saga of K2-18b is, above all, a story of hope tempered by caution and driven forward by humanity's unquenchable hunger for truth. Over the coming decade, the James Webb Space Telescope will keep its unblinking golden eye fixed on this distant water world, gathering more hours of precious starlight filtered through its alien sky. Whether the fragile dimethyl sulfide signal blossoms into a 5 sigma triumph or quietly dissolves into instrumental noise, K2-18b has already carved its name into the history books. It is the planet that dragged the search for life out of the old Earth-centric playbook and forced us to confront a galaxy filled with ocean worlds we never imagined. It is the world that whispered, however softly, that the most ordinary planets around the most ordinary stars might also be the most alive. The Hycean frontier now stretches before us like an endless dark sea under red starlight. Somewhere out there, the chemical scent of distant plankton may already be drifting. The universe is holding its breath, waiting to see how boldly we answer. To truly feel the weight of this moment, we have to step back and walk the long road that brought us here. A road that begins not in observatories, but around ancient campfires, when the first humans looked up and wondered if anyone was looking back. For most of human history, the question of life elsewhere was pure philosophy. Epicureans in ancient Greece argued that an infinite universe must contain infinite worlds, many of them inhabited. Aristotle countered that Earth sat alone at the center of creation. The debate raged for 2,000 years with no way to settle it, until Copernicus, Kepler, and Galileo yanked our planet from its throne and scattered possible worlds across the heavens like sparks from a fire. The telescope turned speculation into exploration. Galileo's first glimpses of Jupiter's moons and Saturn's rings proved that not every light in the sky circled Earth. When 19th century telescopes revealed the ice caps and seasonal darkening on Mars, imagination caught fire. Percival Lowell, gazing from his private observatory atop a dark Arizona hill, sketched intricate webs of canals, straight lines too perfect to be natural, carrying precious water across a dying red desert. Newspapers screamed of a Martian civilization fighting for survival. H.G. Wells wrote of their desperate invasion. The public devoured every word. Only later, with better instruments and spacecraft flybys, did the canals dissolve into nothing more than optical tricks and the brain's stubborn habit of finding pattern in chaos. Mars, it turned out, was a graveyard of shattered hopes. The dream refused to die. It simply changed frequency. In 1960, Frank Drake pointed a 26-meter radio dish at the stars Tau Ceti and Epsilon Eridani, listening for the deliberate chatter of another technological species. Project Ozma heard nothing but silence, yet it birthed the modern search for extraterrestrial intelligence. A year later, Drake gathered the world's sharpest minds in a small room at Greenbank and wrote down a formula on a blackboard that still haunts every astrobiologist. This formula set out to answer a single question: how many communicative civilizations are out there right now? The Drake equation turned a philosophical longing into a scientific shopping list of unknowns, a list of factors we need to figure out, and we have been filling in the blanks ever since. From the canals of Mars to the tentative spectral wobble of dimethyl sulfide 120 light-years away, every generation has chased the same question with the best tools it had, only to watch most signals fade into illusion or noise. Yet each disappointment sharpened the method, raised the bar, and pushed the frontier a little farther out. K2-18b is simply the latest, most sophisticated chapter in that ancient story. The universe has tested us before and found us eager to believe. This time, we are older, wiser, more careful, and the whisper we think we hear is coming from an ocean that might cover an entire world under a blood-red sun. The silence is no longer quite so complete. For decades, the search for extraterrestrial life meant one thing: SETI, giant radio dishes tilted toward the stars, straining to catch a deliberate beacon, a snippet of alien primetime television. Anything that said, "We are here." Billions of hours of sky were scanned, millions of frequency channels monitored, and the result was an aching cosmic silence. No signals, no greetings, nothing but the quiet hiss of the universe itself. That silence gave birth to the Fermi paradox, Enrico Fermi's famous lunchtime question in 1950. If the galaxy should be teeming with intelligent life, where is everybody? The paradox has haunted us ever since, a cold reminder that high probability and total absence can sit uncomfortably side by side. Everything changed in the 1990s when astronomers learned how to spot planets around other stars. Suddenly, we weren't just listening anymore. We were looking for the subtle chemical breath of simpler life. Microbes drifting in alien seas, forests exhaling oxygen on distant continents. The Kepler Space Telescope, launched in 2009, delivered the knockout blow to cosmic loneliness. Planets are not rare curiosities, they are the rule. On average, every single star has at least one world in orbit, and many have entire families. In the Milky Way alone, that adds up to hundreds of billions of potential cradles for biology. The sheer statistical weight became impossible to ignore. Life, even simple life, should be everywhere. K2-18b and the James Webb Space Telescope represent the moment all of that promise finally collided with reality. We stopped merely counting planets and started reading their air. For the first time, we are tasting the chemistry of worlds orbiting other suns, hunting for the faint chemical perfume that only life seems capable of producing. This is the exoplanet revolution, reaching its mature, breathtaking phase. And at the center of that revolution floats the most sophisticated machine humanity has ever flung beyond Earth: the James Webb Space Telescope itself. Webb is not merely big, it is an engineering miracle operating at the ragged edge of what physics allows. Its golden primary mirror, 18 hexagonal segments of beryllium coated in a whisper of real gold, spans 6.5 meters, unfolding in deep space like an origami flower, because no rocket on Earth could launch it already open. Those segments must hold their shape and alignment to within a few billionths of a meter while floating 1,000,000 miles from home, in perpetual darkness and cold. That cold is everything. Webb is an infrared telescope designed to see heat itself. To keep its own warmth from blinding its detectors, the observatory is chilled to a mere 40 degrees above absolute zero, shielded from the sun by a 5-layer sunshield the size of a tennis court that flutters like a silver kite in the vacuum. In that frozen silence, Webb drinks in the faint infrared glow of the universe's infancy, the first stars igniting after the Big Bang, and, almost as an afterthought, uses the exact same superpower to read the air of planets too far away to ever visit. When starlight filters through an exoplanet's atmosphere, molecules like methane, carbon dioxide, water vapor, and, crucially, dimethyl sulfide snatch away specific colors of infrared light, the way stained glass steals pieces of a rainbow. Hubble could only glimpse the brightest, broadest hints in visible and ultraviolet wavelengths. Webb, basking in the infrared dark, sees those molecular fingerprints sharpened to razor clarity. It is the difference between trying to read a letter through frosted glass and holding it under a spotlight. We built a machine that can smell alien oceans from 100 light years away. And in the thin, hydrogen-rich sky of K2-18b, it may have just caught the first whiff of something alive. The dimethyl sulfide detection, if it holds, owes everything to Webb's mid-infrared instrument, MIRI, a masterpiece of cryogenic engineering that stares into the part of the spectrum where DMS screams its presence loudest. At wavelengths stretching from 5 to 28 microns, the molecule's carbon-sulfur bonds vibrate like tuning forks, carving unmistakable notches into the starlight that has traveled 120 light-years to reach us. To pull that fragile signature out of the cosmic static is nothing short of sorcery. We are sniffing the breath of a possible biosphere across a gulf so vast that the photons we caught left K2-18 before modern humans even existed. Yet this same triumph is the seed of the controversy. MIRI is exquisitely sensitive, but it is also exquisitely fragile. Its detectors operate just 7 degrees above absolute zero, and even the tiniest thermal twitch inside the telescope can masquerade as an atmospheric feature. The raw data stream is a tangled symphony of starlight, planetary glow, cosmic rays, and the instrument's own heartbeat. To tease out the atmosphere's whisper, scientists must run the numbers through a gauntlet of mathematical filters, subtracting backgrounds, flattening detector artifacts, modeling the star's own spectral quirks. Change one assumption, tweak one parameter, and the DMS line can swell into view or vanish like smoke. That is exactly what happened. The original team, led by Niku Madhusudan, chose a pipeline that carefully preserved the tentative signal. Independent groups, applying equally rigorous but slightly different pipelines, watched the same line shrink to insignificance or disappear entirely. No one is accusing anyone of misconduct. This is simply science colliding with the bleeding edge of detection. When you are trying to read a molecule smaller than a virus on a world 1,000 trillion kilometers away, the difference between discovery and mirage can hinge on how aggressively you smooth a handful of noisy pixels. This is the reproducibility frontier of 21st century astronomy. Not a crisis of dishonesty, but a natural consequence of pushing human technology into realms it was never designed for. The community is already responding, forging standardized community pipelines and open source benchmarks, a kind of Rosetta Stone for mid-infrared exoplanet spectra. So the next time a biosignature candidate appears, the entire world can reduce the data the same way and either celebrate together or move on together. K2-18b is teaching us, in real time, how to hunt for life without fooling ourselves. And that lesson matters because the prize is so much bigger than one planet. The very idea of a Hycean world is a direct assault on everything we once called the Goldilocks zone. For decades, we drew neat circles around sun-like stars and declared only rocky worlds at Earth-like distances could be just right for life. Hycean planets laugh at that cartoon. Their colossal hydrogen blankets act as super greenhouse cloaks, trapping heat so efficiently that a liquid ocean can stay warm even on the frigid outer edge of a star system. Or, in the case of red dwarf planets like K2-18b, survive the wild temperature swings of tidal locking. More radical still, these worlds may not need continents at all. Life could be entirely pelagic, floating or swimming in a global sea that has never known a shoreline, never felt wind or rain, never seen a sunset. The chemistry would be alien, perhaps slower, perhaps stranger, but the volume is staggering. A single Hycean ocean could hold more living space than all of Earth's seas combined, buried under a sky no creature ever evolved to look up at. If this model is right, the classical habitable zone was never the main story. It was the exception. The real estate where life is most likely to flourish might be these dark, brooding water worlds wrapped in hydrogen quilts, orbiting the most common stars in the galaxy by the hundreds of billions. K2-18b is not just a data point, it is a paradigm fracture. And whether the DMS whisper turns out to be biology or noise, the crack it opened will never close again. The universe just got a lot bigger, a lot wetter, and, perhaps, a lot less lonely. The Hycean concept strikes at the heart of one of astronomy's most humbling ideas, the principle of mediocrity. Earth is not the crown jewel of creation. It is just one data point in a staggeringly vast sample. If a planet twice our size, wrapped in a crushing hydrogen blanket and orbiting a flickering red dwarf, can still cradle a global ocean full of life, then the old, rare Earth argument collapses like a house of cards. The galaxy is not merely peppered with planets. It is absolutely flooded with potential living worlds that look nothing like the pale blue dot we call home. Hundreds of billions of red dwarfs, each likely nursing at least one sub-Neptune in the right temperature range, suddenly become hundreds of billions of possible birthplaces for biology. Mediocrity has never felt so exhilarating. Yet these same worlds come with brutal caveats. Plunge deep enough into a Hycean ocean and the pressure skyrockets, hundreds or even thousands of times greater than at the bottom of the Mariana Trench. Water itself begins to behave strangely. At those extremes, it freezes into exotic forms like Ice 7, a dense, hot ice that stays solid even at temperatures well above boiling on Earth. This high-pressure ice sheet could form a lid on the seafloor, sealing the ocean off from the rocky mantle below. No more seafloor volcanism spewing nutrients, no more subduction zones recycling carbon, no plate tectonics at all. On Earth, plate tectonics is the quiet hero of long-term habitability. It powers the carbon silicate cycle. Volcanoes release CO2, rain washes it into the oceans, rocks lock it away, subduction drags those rocks down to be melted and release the gas again in a billion-year thermostat that has kept our planet from freezing or frying. Cut off that cycle and most worlds drift toward climate catastrophe. Either snowball or greenhouse hell. A Hycean planet sealed under its own ice roof might be exactly that kind of dead end, a place where life can spark, maybe even flourish for a while, but eventually choke on its own waste or freeze when the star dims, so any biosphere on K2-18b would have to play by different rules. Perhaps the sheer immensity of its ocean, thousands of kilometers deep, acts as a planetary shock absorber, buffering temperature swings for billions of years. Perhaps the hydrogen atmosphere drives a completely different geochemical cycle we haven't even imagined. Or perhaps the life itself has become the thermostat. Vast microbial communities that collectively engineer their environment, pumping out or sequestering gases on a global scale, turning the entire ocean into a living, self-regulating superorganism. That would be the ultimate biosignature, not just a molecule, but a planet that refuses to die because something down there is actively keeping it alive. This is why K2-18b matters so desperately. Confirm life there and you have a second Genesis, an origin of life completely independent from our own. Two separate rolls of the cosmic dice, both landing on biology, would prove that life is not a miracle, but a routine chemical outcome, whenever water, energy, and time coincide. The leap from one known biosphere to two would be the single greatest intellectual earthquake in human history. Every philosophy, every religion, every story we tell about being special would have to be rewritten overnight. That is the prize riding on a handful of noisy infrared pixels from a telescope floating in the dark 1,000,000 miles from home. The story of K2-18b is the story of astrobiology finally growing up. We have left the era of campfire speculation and entered the age of spectra, of hard, cold data wrested from starlight that left its source before any human being had ever looked up and wondered. We are no longer asking, could life exist? We are demanding the universe show its cards. And for the first time, across 120 light years of silence, it just might have blinked. The answer, for now, is still the faintest of whispers, a chemical trace drifting across 120 light years of emptiness. But every new observation adds volume to that whisper, and the ancient silence that has greeted every generation before us is beginning to fracture. K2-18b is also, at its core, a story about the humble red dwarf stars that dominate our galaxy. These dim, cool suns make up roughly 3/4 of all stars in the Milky Way. Hundreds of billions of them scattered like embers across the spiral arms. If even a small fraction of their planets turn out to be Hyson worlds with stable, life-bearing oceans, then the galaxy is not merely hospitable in places, it is practically saturated with potential biology. Yet red dwarfs are anything but gentle nursemaids. In their turbulent youth, and sometimes well into middle age, they unleash monstrous flares, sudden eruptions that can briefly double the star's brightness and flood nearby planets with X-rays and ultraviolet radiation strong enough to strip a thin atmosphere bare. A naked rocky world would be scoured clean. The Hycean shield of thick hydrogen and a global ocean may be the only thing that saves the day, absorbing and diffusing the onslaught before it can sterilize the depths. Any life that calls K2-18 home would have to be forged in fire, supremely radiation resistant, perhaps even radiotrophic, organisms that treat those deadly stellar tantrums as an all-you-can-eat energy buffet, or that cloak themselves in pigments darker and more efficient than any melanin we know. This realization has sparked an entirely new branch of astrobiology, stellar flare resilience. Labs are simulating red dwarf hellfire on microbial cultures, modeling how deep the killing radiation penetrates a hydrogen-rich atmosphere, and calculating whether periodic apocalypse might actually accelerate evolution by constantly reshuffling the genetic deck. Whatever swims in that hidden ocean would not be fragile. it would be the toughest life the universe has ever cooked. K2-18b stands as living proof, whether literally living or not, that nature is infinitely more inventive than our parochial imaginations. It mocks our old certainties about what a habitable world must look like: rocky, Earth-sized, sunlit, with neat continents and blue skies. Instead, it offers a dark, pressure-crushed sphere wrapped in hydrogen, orbiting a star that flickers like a dying lantern. And it forces us to confront the exhilarating possibility of a truly universal biology, one that writes its own rules on whatever canvas the cosmos provides. The journey here has already rewritten the playbook. It has drilled caution and skepticism into our bones, reminded us that the greatest claim in science must survive the fiercest scrutiny, and shown just how razor-thin the line is between breakthrough and illusion when you are tasting alien air from 1,000 trillion kilometers away. Yet the deepest echo of K2-18b is not scientific. It is existential. For the first time in human history, we are not merely asking the ancient question into the dark. We are straining to hear an answer. A tentative 3 sigma hint of dimethyl sulfide is still only a ghost of a possibility, but it is the clearest ghost we have ever caught. And ghosts have a way of reshaping everything we thought we knew about being alone. For centuries, that question, "Are we alone?" has been the lonely province of poets and priests. K2-18b is the moment the universe finally leaned in close and, ever so softly, whispered back, "Maybe not." That faint 3 sigma whisper from a world 120 light-years away carries a force far greater than any headline. It is the kind that can pull humanity's gaze upward, away from borders and flags, and remind 8 billion people that we share something infinitely larger than our differences. A fragile planet, a curious mind, and a universe that might be full of company. The search for life on K2-18b is no longer just equations and spectra. It is the oldest human quest dressed in the newest clothes, a philosophical pilgrimage to discover whether consciousness is a solitary accident or the natural echo of the cosmos itself. Hope, caution, and the stubborn pursuit of truth. That is the true story of K2-18b. Over the next decade, the James Webb Space Telescope will return to this distant ocean world, again and again, stacking hour upon hour of precious starlight, until the dimethyl sulfide line either sharpens into undeniable reality or fades into the noise of instrumental ghosts. Confirmed or refuted, the outcome hardly matters for its legacy. K2-18b has already rewritten the textbook. It has shown us that the most ordinary stars, the dim red dwarfs that outnumber all others, may cradle the most extraordinary habitats. It has turned the old narrow Goldilocks zone into a vast, unexpected archipelago of possible life. The Haitian ocean world is the new frontier, a dark, brooding, hydrogen-shrouded sea where biology might write itself in rules we have barely begun to imagine. Somewhere out there, the chemical scent of distant plankton may already be rising. The universe is no longer a silent auditorium. It is a stage, and we have just heard the first rustle of movement in the wings. K2-18b asks the ultimate question of cosmic destiny. If life can bloom on a planet so utterly unlike Earth, then the galaxy is not a sterile desert broken by one miraculous oasis. It is a garden, wild, varied, and very much alive. The silence we mistook for emptiness may simply be the silence of distance, of countless voices speaking in languages of chemistry and light we are only now learning to hear. The James Webb Space Telescope is humanity's ear pressed against the door of the universe, and K2-18 B is the first faint melody slipping through the crack. The search goes on. The most thrilling chapters of our story are still unwritten, waiting in the atmospheres of 1 trillion worlds we have yet to name. Thank you for joining us on this voyage to the edge of everything we know. This is Cosmo Depth. Until the next whisper becomes a roar, keep looking up.